Hey, welcome back. So this is 9.4, and what we're doing is developing all these tests that are going to tell us whether or not a given series is convergent or divergent, and we're thinking that convergence means useful, divergence means kind of not useful or useless. Okay, so let's dive right in. So 9.4, let's find my pen, make sure it's ready. It's comparison of series. And the concept is kind of like this. You'll have some series such that you know it's going to converge or diverge. So like 1 all over n to the 7th. This thing is a p-series. Its p-value is 7, and therefore it's convergent. Okay? So you kind of have this series that you know about its behavior, usually a geometric or a p-series. And then somebody throws in your lap something that looks an awful lot like that series. So maybe 1 over n to the 7th plus n. Okay, and you want to say, well, this is kind of the same thing as a p-series, p equals 7, but you really can't do that. Okay, you need to be a bit more careful in your work, and that's where the comparison of series will come into play. So the first type of comparison is the direct comparison. And I think what I'll do is show you some examples and then kind of hit the proof of it. My proof ability is not, well, I mean, I had this approach to proofs where I want it to be all encompassing and basically handed down from Mount Olympus, you know. And if it's anything less than that, my brain just does not, want to work with it. So please bear with me as I go through some of these proofs. If you want perfection, go look, well, quote unquote perfection, go look in the book. And okay, so that being said, what is the direct comparison test? We're going to have two series that we're comparing. Just call one a sub n, the summation of a sub n, the other one the summation of b sub n. Then if we can construct this inequality where all of the terms of this first series are greater than 0, so they're all positive terms, and then they're less than or equal to the terms of the second series, and this holds for all n eventually. Then we have these kind of conclusions that we can have. So if the series with the bigger terms converges, then the series with the smaller terms converges. Okay, this is kind of related to what we did with, there was one question in the homework in 8.8 where we said basically if you have this improper integral, the integral from maybe 1 to infinity of f of x dx, and you know that that thing is convergent, then any sort of integral of a curve which is below that will also end up having to be convergent. So say this is g of x, then g of x dx will also be convergent. But you have to have that top curve converging in order to get this bottom convergent. Okay. And you can think of it kind of just visually speaking, going from 1 to infinity. If the area underneath this f of x is finite, then you would expect the area underneath g of x to be less, and it's going to be finite. So it's the same idea here. So from the integral test with our work there, we kind of saw that there's a correlation between summations and integrals, and this is kind of a continuation in some ways. But anyways, if you have the reverse situation, if the series a sub n diverges, it'll force the series above it to diverge as well, so to speak. So if the series a sub n diverges, then the series b sub n will diverge. And we had the same thoughts in that one question in 8.8 as well. So if that blue curve, if that has infinite area underneath it, then you better bet the black curve is going to have infinite area underneath it as well. Okay, so the process for doing the comparison test, the way I want it on my actual examinations is to do like a 3-point method. Okay, so first you're going to make a comparison with an inequality. Second, you're going to talk about the series you're comparing it to. And then third, you're going to make your conclusion. Okay, so let's apply that process to problem 1 in the book or in Web of Science. So I have the sum from 1 to infinity of 1 all over 3n to the 7th plus 6. Okay, and I'm going to compare it to this series 1 over 3n to the 7th. So it's a little bit like what we did with determining limits when you have infinity over infinity, when you have rational functions, so a polynomial over another polynomial, just circle the high degree terms. That's kind of what we're going to do here. Okay, but anyways, your first step is to make a comparison between the terms of the given series and the terms of this other series that you're creating. Okay, so in this case, I've chosen to create 1 over 3 n to the 7th, right? Okay. So what is the comparison between these two series? Which one is bigger, which one is smaller? Well, you can kind of think of it as going from here to here, I made the denominator smaller, therefore I made the entire expression bigger. So you'll have that inequality hold. If you don't like that, you can kind of cross multiply and then make the relationship. So if I multiply both sides by 3n to the 7th, I would have 3n to the 7th plus 6, and then I'm comparing that to 1. And of course, you have something small over something bigger, that's going to be less than 1. So that also would give you the inequality that you do this part over here in your head, right? And then that would tell you, okay, I need a less than symbol here. Okay, so for our test to work, we need this new series to be hopefully convergent. Okay. So step 2, I investigate this new series that I've created. What kind of series is it? Well, it's a constant multiple of a p series, right? And I had sort of this statement earlier, I think maybe in 9.2, where I said basically the sum of a sub n and the sum of some constant, non-zero constant, times a sub n both have the same behavior. Okay. So although it's not exactly the p series, it's a constant multiple of it. And it'll have the same behavior as the p series. So you could say something like that. It's a constant multiple of p series. The p value here is 7, and therefore it's convergent. And that's what we need for this to hold. Please note that it won't always hold. For instance, if going back to our picture here with the black and the blue curves, if that black curve is divergent, it says nothing about this curve below it, right? If the area underneath the black curve is infinite, the area underneath the blue curve may be either or, right? And you don't see those conclusions in our set of conclusions. I mean, there's 4 possible conclusions, right? We don't include if the series b sub n diverges, then the series a sub n diverges. We don't include that because it's just not, you can't make that conclusion, okay? So the way we have it here is that the top curve has to be, for it to be useful in this instance, that for the top curve to be useful, it has to be convergent, and that's what we have here. So if the top curve is convergent, then both will converge. Okay, great. Let's look at some other examples of this. Let's make sure I'm not shortchanging you here. Just one, maybe, a comment. Let's see how I want to do this. No, we'll move on. Okay, so let's not overcomplicate things. Okay, so number 2 in the homework, n equals 2 to infinity. 1 all over n to the, I think it's 6/7 minus 1. Okay, so same process. You're kind of comparing it to a known series. Usually you could chop part of it off, but there's other ways if the inequality doesn't work the way you want it to. You can kind of compare it to something that's similar. So for instance, I guess I'm going to have to go into this issue just a little bit. Let's say I had, for example, the sum of I don't know, 1 all over 2n plus minus 3, okay? Or maybe even, I don't want to go that direction. I want 2n squared minus 3. Okay, so I believe in the first step you would say, all right, let's do this comparison. I'm probably going to compare it with 1 all over 2n squared, which is a constant multiple of the p series, p equals 2, and it's convergent, right? The problem here is probably the inequality, right? Because here you've had to increase the denominator, therefore you decrease this expression, and then the curve on top doesn't have what we want, okay? In this case, it's the curve that's kind of below is convergent, and that won't give you any conclusions about the curve above. So going back to the black and blue here, if the amount of area underneath the blue curve is finite, it doesn't really tell you anything about the amount of area underneath the black curve. Okay, so having this direction of the inequality is kind of useless. So if you have, in here, this would be 2n squared. P series is a constant multiple of the p series, but p series nonetheless. P is 2, so therefore it's convergent. But you can't make a conclusion, okay? Okay, so it's not always going to be a matter of kind of just circling the high portions, the big parts. In this case, what you would need to do is add something in. Okay, so what am I going to do? I'm going to go, let's say, 2n squared. So what do I want to do? I would rather subtract, right? So minus an n squared. I think that would work because for n values greater than 2, this side on the right is going to be now greater than, right? So if you cross multiply it again, we could compare it. So I'd have 2n squared minus n squared all over 2n squared minus 3. And I think that's pretty clear then that this is just going to be n squared all over 2n squared minus 3. And then once you get past 2, the denominator is going to be greater than the numerator, right? So, and then, what is this thing? It's 1 all over n squared. So secondly, then you have the series 1 over n squared. It's p series. It's clearly p equals 2, so it's convergent. And then once you get it, restricted over top, then you could say both converge. Okay, so you will have to be a little bit creative with what you're doing, but hopefully those two methods, either kind of, chopping off part or adding something in, will get you to what you need. Okay, so anyways, let's look at number 2 here, getting you back to reality. And I don't think the book does a great job of teaching you how to do these inequalities. I think I don't know what they're thinking. They sell the same book over and over. They make one little change every year, so they're getting away with murder. But they really need to teach this section better and illustrate it with more of these kind of methods. But anyways, let's take a look at this guy. And I think the chopping method will be the method to go with here. So I have n to the 6/7 minus 1, and I want to compare that to 1 all over n to the 6/7. So I know that series that I've just created is just a p series where the p value is equal to 6/7, and so that's divergent. And so I need that to be less, I need that to be below, right? So hopefully that will hold true. And it is true. So if you were to, again, either cross multiply or compare the denominators, you would have n to the 6/7 all over something smaller, right? You're taking away 1 from the denominator. So the top is bigger than the denominator. So that will be greater than 1 if you want to think of it that way. But the inequality holds in the way we want it. We got the one, so thinking of this black and blue stuff again, The blue curve has infinite area underneath it. Now force the top curve to also have infinite area. So we'll say both diverge. Okay, so step 3 then, both diverge. Okay, great. Let's look at another example. Actually, yeah, sure. So this is kind of more along the lines with what I was doing on the right. So let's see if we can pull this off. 3n to the 7th minus 6. It looks like a convergent p-series, right? So here we go, step 1. And again, you're probably thinking, well, I can just use that for my comparison, but it won't work. So let's put this as the sum of 1 all over 3n to the 7th. Whoops. And you don't really write the summation when you're doing it. It's just the comparison of the terms. It's not the comparison of the series. So if you look back to the original kind of definition of the problem, look, that you don't see a summation symbol in there. And you won't see the summation symbol in any of my first steps. Okay? It's only comparison of the terms of the series. It's not the comparison of the series itself. Okay, so I had 3n to the 7th minus 6. And I want to compare that, I think, to 1 over 3n to the 7th. Okay? But because I know this is a convergent series that I'm comparing it to, I'm hoping that this thing will be above. Right? So it's a constant multiple of the series, is a p-series, so it's convergent, right? Please note what p-series it is. P is 7 in this case. Okay, so I need that thing to be above for the two criteria, one of the two criteria of the whole. Either, it's above and convergent, or it's below and divergent. All right, so in this case, what's going on? I've increased the denominator, therefore I've actually decreased that expression, and I don't have the proper inequality type. Okay, so bummer. So the quiz then is going to be using this process in the purple in order to fix it, right? So you should be able to apply that purple process to get a new inequality for the video quiz. So step 1, you're comparing 1 all over 3n to the 7th minus 6 with, 1 all over 3n to the 7th minus, and then you could template it, hopefully. Okay, so you're thinking this procedure here in order to pull it off, right? And then you should be able to make your comparison work, right? There are some small issues with the n value. Like, for instance, if you let n equal 1, I don't think it would work, right? So back up here in my purple example, this inequality doesn't hold for all n, but it holds for all n eventually, which turns out to be more important than just, is it what happens in the beginning. So, when n is equal to 1, you can see, well, this is 1 all over 2 minus 3 is negative 1. Well, I guess it works. Does it work there? Let's make n equals, sure, let's keep it there. And then on the other side, you have 1 all over 2 minus 1. Well, that one works. Is it going to hold for all n? Let's try n equals 2. Yeah, I think it does. Yeah, it holds for all n. Okay, sometimes it doesn't hold for all n, though. Okay, sorry. So hopefully this one holds. Does this one hold? So I don't think it'll hold for all n. I'll sort of let the cat out of the bag. You're going n to the 7th right here, right? So you're going to have 1 all over 3n's to the 7th minus 6, and you're comparing that with 1 all over 2n to the 7th. So when n is equal to 1, does it work? So you have 1 all over, it becomes negative, so it does kind of work. And then as soon as you put in 2, so 2 to the 7th is some huge number. It's going to have to pan out. Hold on, let me pause the video. Yeah, I don't know what I'm thinking. So sometimes it don't work, but this one is going to work out nice for us. Okay, so your quiz is basically doing the 1, 2, 3. Okay, so and then make your conclusion, and it's this problem right here basically you're doing. Okay. So get your inequality, describe the series that you're comparing it to with the p-value, and your conclusion then should follow. So that's kind of how I want you to do it on the exam. Okay, so that's the video quiz. Let me pause the video so I can write it down. Okay, great. Some more tricky problems that you'll definitely encounter, which basically just takes it's just testing your ability to create these inequalities. You have the ln of n all over n plus 8, and your first step, again, you're creating this comparison with hopefully a known series. And so what do you want to do? Well, it kind of looks like maybe it's a harmonic series you're comparing it to. So 1 all over, let's say, n plus. So what have we done here? First off, the ln of n will be greater than 1 when n is greater than 3. And then the n plus 8, it's we could just say n plus 8 on this side as well. If you don't like that, you can use n plus 8n, right? And of course, that will just be 1 all over 9n. And then that thing is a constant multiple of the harmonic series, which is divergent. Okay. If we automatically know the harmonic series is divergent, so we need not write, p equals 1 p series. For this to hold, we need this inequality to be true. And just by virtue of the fact that that numerator is less than the ln of n eventually, and that should do it. Even if we kept the denominators the same, you would still have this inequality, but we've amped it up. We've then gone from there and increased the denominator, making it even worse. So this case, I think it's pretty clear that both diverge. Okay. Let's look at number 5, another kind of weird one. 1 over n factorial. So what the heck am I going to compare that to? Okay. Well, you're going to compare it to a geometric. And it goes back to the kind of footnote in the book. If you're really reading the book with a microscope, you probably caught this factoid. The limit of 2 to the k all over k factorial is equal to 0. In other words, that k factorial is going to be way bigger than 2 to the k or 3 to the k or 4 to any exponential you can imagine. So the denominator on that left is going to be way bigger than the denominator on the right, and therefore the overall expression for the terms of the series will be much smaller than the terms of a geometric. So from there, you could say, all right, this series is geo with r value 1/2. Therefore, the absolute value of that is less than 1, and therefore it's convergent. Okay. So 90% of the time, you're comparing with p-series, or you're comparing with the geometric. And for those cases and these problems, you need to tell me about the defining characteristics of that thing you're comparing it with. So it needs to be, this is a p-series, p-value is this, convergent or divergent. So you kind of think of these 3 things that I'm always looking for in more than one way, right? So first, there are the criteria, the kind of the testing procedure. This 1, you do an inequality. 2, you talk about the series you're comparing it with. And 3, you make a conclusion. And then within step 2, I want to see those 3 factoids: the type of series, its criteria, and then its behavior. Okay, so hopefully that's clear. As far as the proof goes, the proof is fairly simple. We usually start with the proof of I believe it's the convergent part. So if the series B sub n converges, then the series A sub n converges. And so the proof, we made the supposition that B sub n converges, thus we can call it something, so it'll add up to something, right? So B sub n equals some number s. And then, noting that we have this inequality holding for the terms of the series, we have the sequence of partial sums for A sub n being increasing and being bounded above, which is the monotonic convergence theorem, basically. So S sub 1, talking with regards to the series A sub n, the first partial sum would be A sub 1. And of course, that would be bounded above by B sub 1 less than or equal to, and that would be bounded above by B sub 1 plus B sub 2. And I said B sub 1, but I wrote B sub n. B sub 2 plus B sub 3 plus dot 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 plus B sub n, and that will be less than or equal to that number s. Okay, and then we have this S sub 2 thing, which is equal to A sub 1 plus A sub 2. And because the terms are all greater than 0, that is going to be greater than S sub 1, right? And it's not 0, so it can't even be equal to it. And then on top of that, you have that, again, this thing is bounded above by this summation S. And then so on and so forth. So S sub 3, the third partial sum, A1 plus A2 plus A sub 3 is bounded above by big S. So, so this S sub n sequence, I maybe call it S hat because it's really different. I don't want to confuse it with the summation B sub n, the summation of B sub n. So S sub n hat is bounded above and increasing and thus convergent by the 9.1 theorem, the monotonic convergence theorem. Monotonic convergence theorem. Okay. Okay, great. Right. So we're, and maybe if I didn't make it clear, the sum of A sub n from, I don't know, n equals 1 to k is our S bar sub k. Okay. Okay, so I didn't really make that clear, I guess, in the beginning. But that's it. And then the proof of the other one is the contrapositive. So if you were to negate this statement and reverse the direction of the implication, so you take this one first, but you negate it. So you say instead the sum A sub n diverges. If that's true, then you take the other part and negate that. The sum of B sub n diverges. And that's just the contrapositive. Okay. So be careful not to actually do the converse or the inverse error. I think I've talked about that before. You can't say if the series A sub n converges, then B sub n converges. It just won't work. Okay, it might work, but not all the time. It won't be universal. So anyways, that's kind of the spiel on the direct comparison test. The other test is the limit comparison test. So section 2 then, limit comparison. And this time, let's start off with the proof, just to get it out of the way. So what is the limit comparison test? We'll suppose, first off, that the terms of one series are greater than 0, and the terms of some other series greater than 0. So we're comparing the sum of A sub n and some other summation B sub n. So suppose we have positive, non-negative terms, and then the limit of the ratio of these terms exists. Okay, if that is greater than 0 and finite, then the two series have the same behavior. Okay. Why is that? Well, a little of it comes from the strict definition of a limit. So you have to remember that basically if you have a limit of a sequence equaling something, so in our particular example, the sequence is kind of this weird ratio of the terms of two series. But anyways, if you have it equaling some number L, you know that if you go out far enough past some number N, all the terms will be within some any epsilon ball that you want to think of, any epsilon distance you want to think of. So L plus epsilon and then L minus epsilon. So maybe the terms are kind of jumping all over the place. But once you get past N, you'll be stuck kind of within there. And that's good because in that way, if you do have a positive number L like we have here, you could say that eventually for some number big N, the terms of the sequence A sub n over B sub n will all be greater than 0. Okay, and that's just true because we've supposed that the limit of that ratio is equal to some number L. Okay. So once you've established that, then you could create an inequality that allows you to take advantage of the direct comparison test that we already established. So given the limit is in fact going to this number L, which is greater than 0, and there exists, again, I'm just going to kind of repeat what I already said, there exists an n value such that, st for such that, for all terms A sub n over B sub n beyond big N, or just write big N, we have this inequality A all over N all over B all over N greater than, we could make, let's call this little m and let's call this guy big M. So it's going to be greater than that lower m and then less than this bigger M. And we could also say that little m is greater than 0. And then guess what? We're just going to multiply through by B sub n. So we'll have 0 less than m times B sub n less than A sub n less than big M times B sub n. So we have kind of the inequality from the direct comparison test. So basically, if the series m times B sub n diverges, then it'll force this A sub n to diverge. There's sort of, it's not, maybe I should have done an example first, but I actually have to start with if this B sub n series is going to be the series that I kind of just make up based off of A sub n. So if B sub n, maybe drop the ball here, but if B sub n diverges, then the series M B sub n diverges because it's a constant multiple, and it forces A sub n to diverge. Okay, so like in step 2 with the direct comparison test, this B sub n thing is going to be the series that we compare it to, that we kind of bring to the table. Okay, and then it works the other way around. If you know this series B sub n converges, then the series M times B sub n will converge, and then that will force A sub n to converge. Okay, let's do an example, because I think I probably lost you as soon as I went down that road. But I think my main point here is that a lot of students think that if the limit equals something, it's automatic that both converge. Okay, that you get into the habit where you think if you can get your hands on an answer, it's equivalent to convergence. But that's just not true in this case. They both have the same behavior, regardless, of what this limit is. It's finite, but that doesn't imply that it means that both series converge. As long story short. Okay. So, anyways, let's look at some of the examples. And I think number 8 is a good example. So I have the series n equals 0 to infinity of 1 all over the square root of n squared plus 3. Okay. And for these problems, I generally always just do the chopping kind of. I don't add something into the denominator like I was doing at the direct comparison. So anyways, I'm going to do kind of a 3-step process again. First, I talk about the series I'm comparing it to. So the series I'm comparing it to is basically that b sub n thing right here in this part of the proof. So I'm going to compare with the series 1 all over the square root of n squared, which is equal to the series of 1 over n, which is the divergent harmonic. From there, I'm going to get this, I'm going to form this limit of a sub n over b sub n. You don't have to get crazy with making sure the one on the top is the a sub n and the one on the top is bottom is the b sub n. That don't matter. So I'm just going to put 1 over n over 1 all over square root of n squared plus 3. This will be then the limit of the square root of n squared plus 3 all over n. And then I'm going to do my circling. And of course, that will just be the limit, because I'm going to infinity. Square root of n squared is just n all over n. And that will equal 1, which is greater than 0 and finite. Hence, both of them will diverge. Okay. And it's basically because you could kind of take the series, the terms of the series that you're comparing it to, and put it above or below this a sub n due to the fact that that limit exists. Okay, and that's kind of the key. The limit existing allows you to form this inequality, which will either be a proof of divergence or a proof of convergence. Okay, so in this case we have the limit exists. And we know the one we're comparing it to is divergent, thus the one that the original series is also divergent. So hence both diverge. Okay. So if you get a limit, that don't mean it's good. Okay, that can mean it all it means is they both act the same. Okay, they both are kind of jerks in this case. All right. So number 9. Let's take a look at it. The series of 4 to the n plus 1 all over 7 to the n plus 1. Okay, so first off, I want to compare it to, I think, this. I'm just going to chop off those parts. And I have 4 to the n over 7 to the n. What the heck is that? It's geometric, right? So it's a geo. There used to be a car named a Geo back in my day. Was it a Ford Geo? I don't know. So the absolute value of r is 4/7, that's less than 1, therefore it's convergent. So if this limit works, they both converge. Okay, that's the point. So we get the limit of 4 to the n over 7 to the n all over 4 to the n plus 1 all over 7 to the n plus 1, multiplied by reciprocals. So I get 4 to the n all over 7 to the n times 7 to the n plus 1 all over 4 to the n plus 1. Although it's not a ratio of polynomials, you could still do the circling trick with the high degree portions. This should be an n. Okay, so it's this junk which is going to determine the behavior, and of course that will just equal 1. If you multiply that out, you know, 4 to the n times 7 to the n is the same as 4 times 7, which is 28 to the n, plus 4 to the n, all over 28 to the n plus 7 to the n. And then you could just circle this portion. That'll be the limit of 1, which just be 1, which of course is greater than 0, and finite. Therefore, both of them have the same behavior. Yay. All right, a tricky one. Some tricky ones in the book or in the homework. This dude. Oh boy. So what the heck am I going to compare it to? Well, you may remember limits of the form 0 times infinity. So if you had this limit of n times, or let's say x times sine of 1 over x as x goes to infinity. You remember this guy? That form is infinity times 0. Okay, so what would we do? We would rewrite it as sine of 1 over x, all over 1 over x, and then we could do L'Hopital's on it, and it would pan out. That's the approach we want to take here, and you can kind of see, here's the terms of the series we are given. So let's make this thing the terms of the series that we're comparing it to. So first, we're going to limit compare with this harmonic series. Okay, right, so I can do that limit. I hope I could do that limit. As n goes to infinity. It's always n going to infinity, so if I don't write it, that's what I mean. You could do L'Hopital's here. So you get cosine of 1 over n, and then that's negative 1 over n squared, all over negative 1 over n squared. Those will cancel out, and you just have the limit of cosine of 1 over n, which is cosine of 0, which is uno, okay? Which is definitely greater than 0 and finite. So therefore, we can conclude both diverge. Okay. Okay, that's pretty much the big and the small of it. Thank you for watching as usual, and I'll see you next time.